Good evening, guys. Today we'll be studying seepage analysis, and in seepage analysis we'll study effect of seepage on permeability, effect of seepage on effective stress, quicksand condition. So as in the last lecture we discussed seepage pressure, seepage force. From the last lecture we have seepage pressure as PS is equals to I Z gamma W, where I was the hydraulic gradient given by H by L and Z was the depth of point in the soil sample where we ought to see the seepage pressure. Now there are two types of seepages. One is the upward seepage and the other one is the downward seepage. What happens in the upward seepages we'll see now. As you can see from the figure, here is a soil sample embedded in a frame where water from higher level is coming through like this and going through the soil. This is an example of upward seepage. Now if we ought to find out the change in effective stress at a point say A, then as we know before, if we don't take seepage into account for a moment, then there must be an effective stress already at the point A. Now if we want to find the effect of seepage over effective stress, we can find that effective stress sigma dash nu is equals to sigma T, that is total stress, minus U is pore water pressure, that is U old, minus PS, which is the seepage pressure. So the new effective stress becomes sigma T old minus U old plus PS. U old plus PS is written here as U new. So therefore we can see that the effective stress decreases in upward seepage. This is dangerous in real life as well, as decrease in effective stress will cause settlement in the soil, and if a structure is over that soil, it can lead to some damage. So here are the key points in upward seepage: that the total stress remains constant, because total strength is simply dependent upon the weight of soil solids. That won't change in the presence or absence of seepage. Hence sigma T remains constant in upward seepage. The pore water pressure, though, this increases, as you could see from this term I am highlighting. U old got an increment of PS, hence pore water pressure increases. You can write UN as new water pressure is UO, that is old pore water pressure, plus PS, that is seepage pressure. Now since if pore water pressure increases, then we know that sigma effective stress is nothing but sigma total minus mu. If you increase the mu, that is pore water pressure, the effective stress is going to be decreased. Now the opposite happens in downward seepage. Though total stress remains constant, since as I said, it doesn't matter whether seepage is happening or not, sigma T is totally dependent upon the weight of soil solids, so it won't change. But in the downward seepage, pore water pressure decreases and hence effective stress increases. You can see new pore water pressure becomes U old minus seepage pressure, and effective stress increases by PS, as you can see from this formula. Now this is an example of, you can see from the diagram itself, this level of water is higher and this level of water is lower. So this is an example of downward seepage. From this given example, we'll see in actual what happens to the pore water pressure, to the effective pressure, and to the new effective pressure in general. Here the the difference in the level of water is given by H, which is 5 meters. Gamma saturated of the soil is given as 21 kilonewton per meter cube, and the length of the soil is 8 meters. Now first we'll find out effective stress at point A without seepage. That will be sigma T minus U, where sigma T is total stress and U is pore water pressure. Total stress is simply found by multiplication of gamma. Here in this case it would be gamma saturated of the soil, and Z. Z is the depth at which we ought to find the total stress. Here in this case it would be 3 meters from the diagram, as we can see, while the pore water pressure is calculated by multiplying gamma W into Z, that is unit weight of water, into the depth at which we ought to find the pore water pressure. So from calculations we'll find that sigma effective stress without seepage would be 33.7 kilonewton per meter square. Now when we'll find seepage pressure at point A, it can be calculated with the formula I Z gamma W. Since I is H by L, H here is 5 meters and L is nothing but 8 meters from the figure itself. Z is 3 and gamma W is taken as 9.81 kilonewton per meter square. After calculations, our seepage pressure comes out to be 18.39 kilonewton per meter square. Now with seepage, effective stress, or the new effective stress at A, would be effective stress the older effective stress at A, along with the new seepage pressure. Hence net effective stress with downward seepage increases. Hence its values has increased from 33.57 without seepage to 51.97 kilonewton per meter square with seepage. Hence downward seepage increases the effective stress of soil. Now if you see the pore water pressure, earlier it was simply 9.81 into 3, but with downward seepage it decreases. It decreases from 29.43 to 11.04. Hence pore water pressure decreases in downward seepage. Now consider upward seepage, where water flows from bottom to the top of the soil. We know effective stress with upward seepage can be written as gamma sub into Z minus seepage pressure. Now gamma sub is nothing but gamma saturated minus gamma W. This term is actually nothing but sigma dash old minus mu. So sigma old is nothing but gamma sat z, while mu is nothing but minus gamma w z. If we take out z common, then gamma saturated minus gamma w is said to be as gamma submerged. Hence, in the formula, we see gamma submerged z minus the seepage pressure. Now, if a certain situation arises that gamma submerged, that is your gamma submerged z, becomes equal to the seepage pressure, that is effective stress of soil becomes equal to the seepage pressure, then the net effective stress will become 0. And if it is a cohesionless soil, the term C becomes 0. From the formula of shear strength, which is generally derived from Mohr's circle, which we'll study later, this formula states sigma dash tan phi plus C. If in this formula C is 0 and sigma is 0, hence shear strength of the soil becomes 0. And if shear strength of the soil becomes 0, it tends to behave like a fluid, because it's from fluid mechanics. We know that fluids, the fundamental property that differentiates fluid from any other thing is fluid have no shear strength, they have ability to flow. So this particular situation in which the effective stress becomes 0, the net effective stress becomes 0 when seepage pressure is equal to the submerged weight of the soil, because z and z would be cancelled here. This is called as quicksand condition, or also piping and boiling. So what is quicksand condition? It is not a sand, but it is a condition in which the soil loses its shear strength and behaves like a fluid. So when upward seepage pressure becomes equals to the submerged weight of soil in cohesionless soil, the soil loses its shear strength and the soil behaves like a fluid. The quicksand condition is not found in cohesive soils though, which include fine silt and clay, because C is not 0 in that case. Even if the effective stress becomes 0, the shear strength won't be 0, right? So quicksand condition is only found in cohesionless soils. Now, from the formula, we had gamma sub z is equals to Iz gamma w. Gamma submerged can be written as G minus 1 plus E. IC is G minus 1 plus E. IC is critical hydraulic gradient at which quicksand condition is achieved. Now, from the formula, we can change certain things, because void ratio can be written in the form of porosity as E equals to N upon 1 minus N. So if we put this thing into this formula, we see IC becomes equals to, on solving, G minus 1 into 1 minus N, that is IC. Critical hydraulic gradient for quicksand condition becomes G minus 1 into 1 minus N. Here G is nothing but specific gravity, which is the ratio of unit weight of soil solid and water. Now, to avoid boiling or piping, or to avoid quicksand condition, the hydraulic gradient should be less than the critical hydraulic gradient, and the factor of safety against piping or boiling is given by the ratio IC by I. Factor of safety should be at least 6 for safety. Coarse sand. Let us see what happens in coarse sand and gravelly soil. For coarse sand and gravelly soil, the coefficient of permeability K is generally large, high. So from Darcy's equation, we have Q is discharge equals to KIA. I can be written as Q by Ka. Now since K is high, I will be less. That is, the hydraulic gradient is decreased considerably in case of coarse sand or gravelly soil. So the question of I reaching IC, that is critical hydraulic gradient, in case of coarse sand is not likely, not possible, since large K makes I extremely small for it to reach to the level of IC. Hence coarse sand will not be showing piping or boiling or quicksand condition, that is coarse sand or gravelly soil. Now there is also, now this is the figure I have drawn here to make you see that fine sand has fine particles of soil like this. So for the seepage pressure to make it flow like fluid, it is very easy, but for gravels which has such a large soil, seepage pressure won't be able to push such large soil particles of gravel to flow like it does for the fine soil. Hence practically it is also not possible for gravelly soil to be behaving like quicksand condition to flow. Here in the photograph I have shown how quicksand condition behaves. You can see it is behaving as if an membrane of an elastic membrane which is stretching down with the person's feet going down. Hence it behaves fluidy. Now there are certain theoretical and theoretical methods to prevent piping. I'll discuss it quickly. One is that increasing path of percolation. We know that I is H by L. If you increase L, naturally gradient will go down and it won't be able to reach IC, that is critical hydraulic gradient, and hence quicksand condition won't take place. Hence increasing the path of percolation helps. How do you increase path of percolation? You increase it by increasing the base width of hydraulic structure, providing vertical cutoff below hydraulic structure on providing sheet pile wall, providing an upstream impervious blanket. Here is an example. This is the base of the dam through which seepage can take place. But if we increase the base width of the dam, the length will be increased, hence the gradient will decrease and quicksand condition won't be able to take place. This is an example of cutoff wall. This helps to reduce or stop the flow of seepage. This is used in the dams, in the foundation of dams, in the construction of dams. Again, this is an example using a impervious foundation. In between a pervious foundation, it will stop the seepage, because seepage can be dangerous. Now the second is reducing seepage. How do you reduce seepage? You can reduce by providing an impervious core like clay core. As I have said, cohesive soils, they don't show this seepage. Now the third is providing drainage filter. A drainage filter changes the direction of flow away from the downstream phase. It prevents the movement of soil particles along with water. Hence drainage filter can be used. Then providing protective filter to reduce uplift pressure, ensure sufficient head loss without building excessive seepage pressure. Now, if someone asks you what is the difference between seepage and permeability, then you can say that the flow of water through soil is seepage, while the property by virtue of which the water is able to flow through a soil is permeability. Now, here is a question which I would like to solve. A 1.25 meter layer of sand, specific gravity is given as 2.65, porosity is 35%, is subjected to an upward seepage head of 0.85 meters. What is the factor of safety against quicksand condition or boiling, or factor of safety against piping? So that's how we've solved it. We'll solve it. G is 2.65, porosity is 0.35, L, length of soil is 1.225. All of this is in the question. Hydraulic grade, the H is 0.85. Now factor of safety is calculated by the ratio of critical hydraulic gradient and the hydraulic gradient. Critical hydraulic gradient is given by G minus 1 into 1 minus N, and I is given by H by L. So while by calculation we find that factor of safety comes out to be 1.58. Now in the same question, if it is asked if factor of safety is 3, then what is the permissible seepage head? How do we find it? From the formula itself we can say I is IC by factor of safety. After calculation this comes out to be 0.3575. Now I is nothing but H by L, so H can be calculated as I into L. It comes out to be 0.447 meters. Now it says that if factor of safety is to be increased, make H less or decrease the H. So it means to increase safety in piping, just decrease the H or increase the length of the soil. It will help to reduce the gradient. It won't, so that it doesn't reach its IC. So how do we increase L? We put another layer of soil over the already present soil there. So this was the layer 1 already present. We provide another layer so as to increase the length of the soil. Hence it will decrease the H, it would decrease the I and increase the factor of safety. You can also make an analogy that if we see a pipe bursting water out from somewhere, how do we generally reduce that bursting water from the pipe? We'll generally reduce the pressure from the tap, closing the tap a bit, or we will rather put our feet on our bursting point. Or so this is an analogy that to prevent to have factor of safety against piping or boiling, we either reduce the pressure, difference, or we increase the length. So in the next lecture we will discuss some more points related with seepage. So thank you for today.